Saving programs on tape after entering a program. If you wish to save it on tape, type. Save program name. Program name can be up to 16 characters long. After you hit, the computer will respond with press play and record on tape. Press both the record and play keys on the dataset. The screen will blank, turning the color of the border. After the program is saved on tape, the ready prompt will reappear, indicating that you can start working on another program or just turn off the computer for a while. Saving programs on disk. Saving a program on disk is even simpler. Type. Save program name. 21. The 8 is the code for the disk, so you're just letting the computer know you want the program saved to disk. After you press caret, the disk will start to turn and the computer will respond with SAVIG Progra 11 name. Ready. Print in calculations. Now that you've gotten through a couple of the more difficult opera tie-ins you need in order to keep the programs you like, let's start making some programs for you to save. Try typing the following exactly as shown.
Oh, I forgot the 64. Okay, I did it. Ready.
If you make a typing mistake, use the registered I key to erase the char actor immediately to the left of the cursor. You can delete as many characters as necessary. Let's see what went on in the example above. First, you commanded, the computer to print whatever was inside the quote marks. By hitting caret, you told the computer to do what you instruct, and Commodore 64 was printed on the screen. When you use the print statement in this form, whatever is enclosed in quotes is printed exactly as you typed it. If the computer responded with syntax error, ask yourself if you made a mistake in typing, or forgot the quote marks. The computer is precise and expects instructions to be given in a specific form. But don't get worried, just remember to enter things as we present them in the examples, and you'll get along great with the Commodore 64. Remember, you can't hurt the computer by typing on it, and the best way to learn BASIC is to try different things and see what happens. Print is one of the most useful and powerful commands in the BASIC language. With it, you can display just about anything you wish, include ing graphics and results of computations. For example, try the following. Clear the screen by holding down the registered key and type. Be sure to use the 1 key for 1, not a letter I. Print 12 plus hit type this line.
Try to find a clear screen by holding down the shift. Clear home. Oh no, it's gone. Print 12 plus 12.
What you've discovered is that the Commodore 64 is a calculator in its basic form. The result of 24 was calculated and printed automatically. In fact, you can also perform subtraction, multiplication, division, exponentiation, and advanced math functions such as calculating square roots, etc. And you're not limited to a single calculation on a line, but more on that later. Note that in the above form, print behaved differently from the first example. In this case, a value or result of a calculation is printed, rather than the exact message you entered because the quote marks were omitted. Addition. The plus sign, plus, signals addition. We instructed the computer to print the result of 12 added to 12. Other arithmetic operations take a similar form to addition. Remember to always hit after typing print and the calculation. 23. Downloaded from www.manuals.
Yeah.
Subtraction to subtract, use the conventional minus sign. Type Multiplication. If you wanted to multiply 12 times 12, use the asterisk to represent multiplication.
144 divided by 12 equals 12.
Exponentiation. In a like fashion, you can easily raise a number to a power. This is the same as multiplying a number by itself a specified number of times. The T up arrow signifies exponentiation. Print 12.5248832. Tip: BASIC has a number of shortcut ways of doing things. One such way is abbreviate ing basic commands or keywords. A can be used in place of print, for exam PLE. As we go on, you'll be presented with many commands. Appendix D shows the abbreviations for each and what will be displayed on the screen when you type the abbreviated form. The last example brings up another important point. Many calculations may be performed on the same line, and they can be of mixed types. You could calculate this problem.
Okay.
Up to this point, we've just used small numbers and simple examples. However, the Commodore 64 is capable of more complex calculations. You could, for example, add a number of large figures together. Try this, but don't use any commas, or you'll get an error. If you took the time to add this up by hand, you would get a different result. What's going on here? Even though the computer has a lot of power, there's a limit to the numbers it can handle. The Commodore 64 can work with numbers containing 10 digits. However, when a number is printed, only 9 digits are displayed. So in our example, the result was rounded to fit in the proper range. The Commodore 64 rounds up when the next digit is 5 or more. It rounds down when the next digit is 4 or less. Numbers between 0.01 and 999,999,999 are printed using standard notation. Notation. Numbers outside this range are printed using scientific notation. Scientific notation is just a process of expressing a very large or small number as a power of 10. 1230000000000000001.23 times 10 to the power of 17th. This is the same as 1.23 10t17 and is used just to keep things tidy. There is a limit to the numbers the computer can handle, even in scientific notation. These limits are: largest, plus or minus 1.70141183 times 10 to the power of 38th. Smallest, different from 0 plus or minus 2.938735888 to 39.
Whoa.
Precedence. If you tried to perform some mixed calculations different from the examples we showed earlier, you might not have gotten the results that you expected. The reason is that the computer performs calculations in a certain order. In this calculation, 20 plus 8 halves, you can't tell whether the answer should be 24 or 14 until you know in which order to perform the calculations. If you add 20 to 8 divided by 2 or 4, then the result is 24. But if you add 20 plus 8 and then divide by 2, the answer is 14. Try the example and see what result you get. The reason you got 24 is because the Commodore 64 performs calculations left to right according to the following. First, minus sign indicating negative numbers. Second, T exponentiation, left to right. Third, multiplication and divisions, left to right. Fourth, plus addition and subtraction, left to right. Follow along according to the order of precedence, and you will see that in the above example the division was performed first and then the addition to get a result of 24. Make up some problems of your own and see if you can follow along and predict the results according to the rules set down above. There's also an easy way to alter the precedence process by using parentheses to set off which operations you want performed first. For example, if you want to divide 35 by 5 plus 2, you type. You will get 35 divided by 5 with 2 added to the answer, which is not what you intended at all. To get what you really wanted, try this. 235/5 plus 2, 5. What happens now is that the computer evaluates what is contained in the parentheses first. If there are parentheses within parentheses, the innermost parentheses are evaluated first. Where there are a number of parentheses on a line, such as 7, 121 plus 9, asterisk, 6 plus 1, 147. The computer evaluates them left to right. Here 21 would be multiplied by 7 for the result of 147. Combining things. Even though we've spent a lot of time in areas that might not seem very important, the details presented here will make more sense once you start to program, and will prove invaluable. To give you an idea how things fit in place, consider the following. How could you combine the two types of print statements we've examined so far to print something more meaningful on the screen? We know that by enclosing something within quote marks prints that information on the screen exactly as it was entered, and by using moth operators, calculations can be performed. So why not combine the two types of print statements like this? Semicolon means no space. Even if this might seem a bit redundant, what we've done is simply use both types of print statements together. The first part prints 5*9 equals exactly as it was typed. The second part does the actual work and prints the result, with the semicolon separating the message part of the statement from the actual calculation. You can separate the parts of a mixed print statement with punctuation for various formats. Try a comma in place of the semicolon and see what happens. For the curious, the semicolon causes the next part of the statement to be printed immediately after the previous part, without any spaces. The comma does something different. Even though it is an acceptable separator, it spaces things out more. If you type, the numbers will be printed across the screen and down onto the next line. The Commodore 64's display is organized into 4 areas of 10 columns each. The comma tabs each result into the next available area. Since we asked for more information to be printed than would fit on one line, we tried to fit 5 10-column areas on one line. The last item was moved down to the next line. The basic difference between the comma and semicolon in formatting print statements can be used to our advantage when creating more complex displays. It will allow us to create some sophisticated results very easily. The next step. Up to now we've performed some simple operations by entering a single line of instructions into the computer. Once caret was depressed, the operation that we specified was performed immediately. This is called the immediate or calculator mode. But to accomplish anything significant, we must be able to have the computer operate with more than a single line statement. A number of statements combined together is called a program, and allows you to use the full power of the Commodore 64. To see how easy it is to write your first Commodore 64 program, try this. Clear the screen by holding the registered key and then depressing the CLRHOME key. 0 type new and press. This just clears out any numbers that might have been left in the computer from your experimenting. 40 now type the following exactly as shown, remember to hit after each line. Now, type run and hit watch what happens. Your screen. I will come alive with Commodore 64. After you've finished watching the display, hit IJUM1E to stop the program. A number of important concepts were introduced in this short program that are the basis for all programming. Notice that here we preceded each statement with a number. This line number tells the computer in what order to work with each statement. These numbers are also a reference point, in case the program needs to get back to a particular line. Line numbers can be any whole number, integer, value between 0 to 63,999. 10 print Commodore 64 statement line number. It is good programming practice to number lines in increments of 10 inches case you need to insert some statements later on. Besides print, our program also used another basic command, goto. This instructs the computer to go directly to a particular line and perform it, then continue from that point. +10 print Commodore 64. 20 go to 10. In our example, the program prints the message in line 10, goes to the next line, 20, which instructs it to go back to line 10 and print the message over again. Then the cycle repeats. Since we didn't give the computer a way out of this loop, the program will cycle endlessly, until we physically stop it with the key. Once you've stopped the program, type list. Your program will be displayed intact because it's still in the computer's memory. Notice too that the computer converted the into print for you. The program can now be changed, saved, or run again. Another important difference between typing something in the immediate mode and writing a program is that once you execute and clear the screen of an immediate statement, it's lost. However, you can always get a program back by just typing list. By the way, when it comes to abbreviations, don't forget that the computer may run out of space on a line if you use too many. 33. Editing tips. If you make a mistake on a line, you have a number of editing options. 1. You can retype a line anytime, and the computer will automatically substitute the new line for the old one. 2. An unwanted line can be erased by simply typing the line number. And 3. You can also easily edit an existing line, using the cursor keys and editing keys. Suppose you made a typing mistake in a line of the example. 2. Correct it without retyping the entire line. Try this. Type list, then using the registered and I keys together move the cursor up until it is positioned on the line that needs to be changed. Now, use the cursor right key to move the cursor to the character you want to change, typing the change over the old character. Now hit TM and the corrected line will replace the old one. If you need more space on the line, position the cursor where the space is needed and hit registered and 1 is equal to 111 at the same time and a space will open up. Now just type in the additional information and hit S. Likewise, you can delete unwanted characters by placing the cursor to the right of the unwanted character and hitting the key in asterisk. To verify that changes were entered, type list again, and the correct program will be displayed. And lines don't have to be entered in numerical order. The computer will automatically place them in the proper sequence. Try editing our sample program on page 33 by changing line 10 and adding a comma to the end of the line. Then run the program again. Variables. Variables are some of the most used features of any programming language, because variables can represent much more information in the computer. Understanding how variables operate will make comput ing easier and allow us to accomplish feats that would not be possible otherwise. Imagine a number of boxes within the computer that can each hold a number or a string of text characters. Each of these boxes is to be labeled with a name that we choose. That name is called a variable and represents the information in the respective box. For example, if we say 10x% equals 15, 20x equals 23.5, 30x $_ the sum of x% plus x. The computer might represent the variables like this: x% 15, x 23.5, x $, the sum of x% plus x equals. A variable name represents the box or memory location where the current value of the variable is stored. As you can see, we can assign either an integer number, floating point number, or a text string to a variable. The percent symbol following a variable name indicates the variable will represent an integer number. The following are valid integer variable names: a %, x%, a 1%, nm%. Percent. The dollar following the variable name indicates the variable will represent a text string. The following are examples of string variables: a $, x$, ml$. Floating point variables follow the sum format with the type indi, ktor, al, xy. In assigning a name to a variable, there are a few things to keep in mind. Mind. First, a variable name can have one or two characters. The first character must be an alphabetic character from A to Z. The second character can be either alphabetic or numeric, in the range 0 to 9. A third character can be included to indicate the type of variable, integer or text string, percent or dollar. You can use variable names having more than 2 alphabetic characters, but only the first 2 are recognized by the computer. So PA and partNo are the same and would refer to the sum variable box. The last rule for variable names is simple: they can't contain any basic keywords, reserved words, such as goto, run, etc. Refer back to Appendix D for a complete list of basic reserved words. To see how variables can be put to work, type in the complete program that we introduced earlier and run it. Remember to hit after each line in the program. If you did everything as shown, you should get the following result printed on the screen. Run x% equals 15x equals 23.5. The sum of xj plus x equals 38.5. Ready. We've put together all the tricks learned so far to format the display as you see it and print the sum of the two variables. In lines 10 and 20 we assigned an integer value to x% and assigned a floating point value to x. This puts the number associated with the variable in its box. In line 30, we assigned a text string to x dollar. Line 40 combines the two types of print statements to print a message, and the actual value of x% and x. Line 50 prints the text string assigned to x dollar and the sum of x% and x. Note that even though x is used as part of each variable name, the identifiers % and dollar make x%, x, and x dollar unique, thus representing 3 distinct variables. But variables are much more powerful. If you change their value, the new value replaces the original value in the same box. This allows you to write a statement like x equals x plus 1. This would never be accepted in normal algebra, but is one of the most used concepts in programming. It means, take the current value of x, add 1 to it and place the new sum into the box representing x. If, then, armed with the ability to easily update the value of variables, we can now try a program such as what we've done is introduce 2 new basic commands, and provide some control over our runaway little print program introduced at the start of this chapter. If, then add some logic to the program. It says if a condition holds true then do something. If the condition no longer holds true, then do the next line in the program. A number of conditions can be set up in using an if then statement. Symbol meaning less than greater than. Equal to not equal to greater than or equal to equals less than. The use of any one of these powerful 10 CT equals 020. Commodore 64-inch 30 CT equals CT plus 140 if court 5 then 20i. 50 end. In the sample program, we've set up a loop that has some constraints placed on it by saying, if a value is less than some number then do something. Line 10 sets court, count, equal to 0. Line 20 prints our message. Line 30 adds 1 to the variable CT. This line counts how many times we do the loop. Each time the loop is executed, CT goes up by 1. Line 40 is our control line. If CT is less than 5, meaning we've executed the loop less than 5 times, the program goes back to line 20 and prints again. When CT becomes equal to 5 indicating 5 Commodore 64s were printed, the program goes to line 50, which signals to end the program. Try the program and see what we mean. By changing the CT limit in line 40 you can have any number of lines printed. For next loops, There is a simpler and preferred way to accomplish what we did in the previous example by using a for. Next loop. Consider the following.
Ten for count equals 1 to 5. And what? 20. Print. Commodore 64. 30 next. See, count. Oh.
As you can see, the program has become much smaller and more direct. CT starts at 1 in line 10. Then, line 20 does some printing. In line 30. 39. Downloaded from www.
Stop it.
Downloaded from www. CT is increment by 1. The next statement in line 30 automatically sends the program back to line 10 where the for part of the for next statement is located. This process will continue until CT reaches the limit you entered. The variable used in a for next loop can be incremented by smaller amounts than 1 if needed. Try this. If you enter and run this program, you'll see the numbers from 1 to 10 by 0.5 printed across the display. All we're doing here is printing the values that NB assumes as it goes through the loop. You can even specify whether the variable is increasing or decrease ing. Substitute the following for line 10.
What do you know? It's time. Yep.